Let's take a look at some examples and counterexamples of group actions. I'm hoping that you have taken a moment off to recollect the definition of group actions, kernel of a group action, faithful actions, and permutation representation. If you haven't, pause the video, take a moment to recollect those ideas. Now, take some more moments off to refresh yourself about different things you know about symmetric groups of degree n, that is Sn, dihedral group of order 2n, that is D2n, in particular D8. Jogging through your memory. Suppose G is acting on a set A. Then there is an analogous homomorphism from G to SA called permutation representation. They are one and the same, described in two different terminologies. That's like how linear transformations are analogous to their matrix representation. Let's remind ourselves about a thing or two about kernels. Kernel of a group action is equal to kernel of phi, that is the associated permutation representation. Remember that the permutation representation is a homomorphism, which is also equal to intersection of all stabilizers of A. Something that you already know, an action is faithful if the kernel contains just the... I'm not going to tell you the answer now. I know you have already recollected it earlier. Let's look at some interesting examples of group actions. The first example, consider G is equal to Sn acting on the set A is equal to finite set 1 to n. Given as sigma dot I is equal to sigma of I for all I belongs to A. Since sigma is the permutation of A, sigma of I belongs to A. The associated permutation representation would be phi of sigma is equal to sigma, or better known as the identity map from Sn to Sa. Here A is the finite set 1 to n, hence Sa will be nothing but Sn itself. Stabilizers for this group action will be Gi is equal to, G belongs to G such that G dot I is equal to I. Here G is Sn, which contains all permutations. That is, stabilizers would be, stabilizer of I will be nothing but sigma belongs to Sn such that sigma dot I is equal to I. You look at the permutation, I fixes I. Rest of it are permuted. Note that the collection of permutations where sigma fixes I, where we are permuting all the other numbers, that is n minus 1 numbers, or it can be more precisely said as Gi is isomorphic to Sn minus 1. Sn minus 1 will not be equal to Gi, but they will share the same properties. Calculating the kernel is child's play now, isn't it? Kernel is equal to collection of all sigma in Sn, where sigma fixes I in A. 1 goes to 1, 2 goes to 2, and so on, n goes to n. That looks familiar. This is nothing but the identity. So, is this action faithful? Yes! When the kernel is just the identity of the group, we call such actions faithful, if you remember. Recall that D8 is equal to group generated by Rns, where R to the power 4 is equal to E and S square is equal to E. Identity, let's call it E for now, is a square with labels as shown here. Rotation of this square clockwise by pi by 2 radians or 90 degree is denoted by R. S is a reflection in the line which passes through vertices 1 and 3. The second example, Consider D8 acting on the set of labels of vertices A is equal to 1, 2, 3 and 4. What will be R dot 1? After rotation, 1 moves to the position of 2. That is, R dot 1 is equal to 2. R dot 2, where 2 moves to the position of 3. R dot 2 is 3 and R dot 3 is 4. What about R dot 4? 4 moves to the position of 1. Therefore, R dot 4 is equal to 1. This can be written in cycle notation as sigma r is equal to 1 goes to 2, 2 goes to 3, 3 goes to 4 and 4 goes to 1. Therefore, we can close the cycle here. Again, S dot 1, if you notice 1 and 3 are fixed after reflection along the axis connecting vertices 1 and 3. Now, S dot 1 is equal to 1 and S dot 3 is equal to 3. What about 2 and 4? S dot 2, 2 moves from its original position to the position of 4. Therefore, S dot 2 is equal to 4 and S dot 4 is equal to 2. How do we write it as a permutation? Simple. 1 is fixed, good. 2 goes to 4, 3 is fixed, then 4 goes to 2, therefore we can close it here. You may be asking, then what about sigma SR? You do remember that permutation representation is a homomorphism, therefore sigma SR can be written as sigma S, sigma R, and you know how to play with cycles. That should work well for a permutation representation, don't you think? What about the stabilizers? Stabilizer of 1, G1 is equal to G belongs to D8 such that G dot 1 is equal to 1. Let's see, we need to fix 1 in its position, vertex 1 in its position. Now, in case of identity, things go smooth. Hence, identity is already in the list. What about rotation? No, 1 moves to the position of 2. So will R2, R3 get out of the list. Now what about S? Yes, 1 is fixed. Then SR, SR square, SR cube? No, 1 is running all around in those cases. That's right. It's just 1 and S. The subgroup 1, S. Better written as the subgroup generated by S. Not that this stabilizer is a subgroup, but not a normal subgroup. I gave away the secret on how to find the stabilizer of 1. Can you help me find the stabilizers G2, G3 and G4? Kernel is given by those elements in D8 that fixes all vertices. And there's only one such. Drum rolls, please. Only the identity. Now, is this particular action faithful? Yes. You know why? Now, what did we just do? We just used group actions to associate the permutation representation to the elements of D8. Shh! Don't tell them that we did it without using group actions already. But see how something which looked intuitive back then is made mathematical through group actions. The third example. Let's again label the vertices 1, 2, 3 and 4. Consider D8 acting on the set of pairs of vertices 1, 3 and 2, 4. So in this case, we take the opposing vertices like this. The group action is given by r dot 1 comma 3 is equal to, that's right, in place of the combination 1 3 you have 2 and 4, the set 4 2, and this is a set, therefore this is nothing but 2 comma 4. Wait, we already gave it the label 2 bar. Then I'll give you a moment to guess. What's r dot 2 comma 4? You guessed it right. 1 comma 3, which is nothing but 1 bar. Take a look at s. S dot 1 comma 3 is equal to, same, that is 1 bar itself. But, and then s dot 2 comma 4, they flip. We do have 4 comma 2, but again this is nothing but 2 comma 4 because it's a set, and this is nothing but 2 bar. Interessante. Basically, sigma r will be permuting between 1 bar and 2 bar, while sigma s is the identity. What about the stabilizers? I am not going to give you the answer. I'll tell you how though. Pick each ANA, 1 bar and 2 bar. Find the element in D8 for which G dot A is equal to A. Don't tell anyone that I gave you the answer for this one too. GA is equal to S comma R square for all A belongs to A. Things are going well so far, isn't it? Thus, the kernel will be equal to the intersection of all stabilizers. Again, another mystery to solve. Faithful? Make a wild guess. Now consider D8 acting on the set 1, 2, 3, 4. That's the vertices in the same level. Just a minor change, isn't it? Let's look at this map this way. What about r dot 1 bar or r dot 1 comma 2? I'll give you a few seconds to guess. In place of the pair 1 2, now you have the pair 4 1. Again, it's a set, therefore it can be commuted, and you will have 4 comma 1, which is equal to 1 comma 4. Hey, codomain should be A, right? Is 1 comma 4 in A? No. Rest you can fill in. Will this be a group action? That's all for now, folks.